All right, hello everybody. We are going to begin section 4.2. Section 4.2 is on the definite integral. So let's get started. If you remember, last time we talked about area under a curve. So we talked about if you have this function, call that function f, and is bounded from a to b, from the interval a to b. It is continuous. So we say if f is a continuous non-negative function, non-negative, so above the x-axis function, and it is on the interval from a to b, then we could say that the area of this region we would call, we have at least been calling S. The area which we will call A of region S. Region S is given by the following sum. It's given by the sum of the rectangles that we are using to approximate the area. So delta x times f of x1 star plus delta x times f of x2 star plus, this pattern continues on till delta x times f of x n star for n rectangles. Okay. Which we could represent as a sum using summation notation as the sum, excuse me, let me leave a little room here, as the sum from I equals 1 to n of delta x times f of x I star. The area is approximated by those two, but if I apply the limit as the number of rectangles goes to infinity, then I get the exact area. And I could apply it to either representation of that sum. I know this is equal to the area A. It is exactly equal to the area A. And that's what we have been talking about prior to this, with a few specifications on that. So you might recall that we would call the intervals that we're dividing A to B up into x0 to x1, x1 to x2, etc. We would call this a partition or a regular partition. Xn minus 1 to xn. This is a regular partition. Regular partition of the interval from A to B. And regular just means all of these intervals are the same length. And the length we get by the term delta x, and it is the right endpoint minus the left endpoint. In other words, the length of this interval from A to B. If I divide that into n rectangles, or n parts, I should say, then I get the base of each rectangle. That is the length of each interval here. So we'll call that a partition. And we would call x1 star, x2 star, x3 star, those points all the way to xn star. We would call these sample points. Sample points. And we've talked about how to find those sample points prior to this, whether you use a right sum or a left sum or a midpoint. Okay. If I have this criteria on my sum, then I can give it a specific name that I've referenced before, but have not, it has not been mentioned in your book up till this point. We would call the sum, we call that sum from I equals 1 to n delta x f of xi star with the above criteria a Riemann sum. A Riemann sum. Riemann was a famous mathematician, so this is named after him. All right. To be a true Riemann sum, that function f is actually not necessarily non-negative. So I might make some notes there. F is not necessarily non-negative. And it can have some discontinuities, but they must be of a specific type that I will get to. Okay? But this is kind of important. It's nice to talk about. What does a Riemann sum give us if a function is below the x-axis? So what does that sum from I equals 1 to n of delta x f of xi star give if f is less than 0? We have examined it when f is greater than 0, but what if f is less than 0? Or say, what if f is greater than or equal to 0 on a portion, on a portion, but not the entirety of that interval AB. And it is negative on another portion. So what if it's partly above the x-axis and partly below? Well, let's examine that. Let us explore. Because we can create some Riemann sums and figure that out. Let's do a simple one. Let's say f of x is equal to -2, and let's consider it on the interval from 0 to 4. And let's just go easy. Let's let n equal 1. So let's only divide that up into one rectangle. So I'm going to graph this function. F of x is equal to -2. -1, -2. This function is constant, so it is a horizontal line. This particular horizontal line here. Okay. And I'm considering it on the interval from 0 to 1. So I'm considering it, or 0 to 4, excuse me. Misread my own writing there. 1, 2, 3, 4. So I'm considering it here. So I am concerned with this area. The area between this function f and the x-axis. Well, what's the area? I can find that. if I only have one rectangle that I'm dividing this up into, then I know the area is equal to delta x times the height of the rectangle, which this is my interval from 0 to 4. So the right endpoint is 4. Delta x times f of 4. My delta x is equal to 4 minus 0 over n, which is 1, which is equal to 4. So the area is 4 times f of 4. Well, f of any value is negative 2, since f is constant. So it's negative 2, which gives me a negative 8. So it appears that it is negative area. Now I'll put that in quotes because that's not really a thing. Negative area. There is no such thing as negative area. But when I use Riemann sums to calculate an area using function values as my heights, a Riemann sum will actually give an area that appears negative if that area is below the x-axis. So I can refer to area below the x-axis as negative area. I'll write that down. That if we use a Riemann sum to find area bounded by a curve for which f of x is less than 0, to find area for which I need to input bounded by a curve, area bounded by a curve, that curve being f of x in this case, for which that function f is less than 0, then we get a negative number. We get a negative number for area. That is just a general rule. Okay. Let's do another example. Let's consider the function f of x is equal to negative x, and let's consider it on the interval from negative 1 to 1. And let's just find area. I am not going to worry about calculating it using rectangles right now, but I am going to use function values. Let's find the area bounded by f and the x-axis. So I'm going to draw a picture of what I have. F of x is equal to negative x if x is 1, y is negative 1. If x is negative 1, y is 1. So this is my function. That's f. And I'm considering the area bounded by that graph of f and the x-axis. So I'm considering this area and this area. Well, just generally speaking, from what I talked about above, if I use a Riemann sum to calculate areas, then this area on the left will have a positive value, and this area on the right will have a negative value. I can just say that by looking at it. Let's see. Let's look at this area. This area is, well, it's a triangle. I can find the area of a triangle by 1/2 times the base times the height, which in this case is 1/2 times the base. In this case is 1. The height is also 1, which I get from a function value. The height I can get by taking f of -1, which is equal to 1/2 times 1 times f of 1, which happens to be 1. So that gives me 1/2. So there's the first one. How about this one? The area is, it is again a triangle, 1/2 times the base times the height, which I'm going to call f of +1, which is equal to 1/2 times the base is again 1, and f of 1 is a -1. So it gives me -1/2. So if I add those two areas together, maybe I'll call this area 1, I'll call this area 2. If I take 1 plus 2, then I get 1/2 plus a -1/2, which gives me 0. In other words, this is what we would call the net area. So it's the difference between area above the x-axis and area below the x-axis. Okay. So it looks like that if my function f is not necessarily above the x-axis, not necessarily non-negative, that a Riemann sum will give us net area. I'll write that down. A Riemann sum for a function f that is not necessarily non-negative, and it is bounded bounded on a to b, gives net area. This is also the case when the limit is applied. And I think that we will we'll stop there for the moment. We will carry on in another video.